Hello, folks. It's your favorite or only neighborhood left-handed physics tutor, and I'm back after a very long hiatus. I think almost 3 weeks um, worth of no videos from me. I apologize. First and foremost, I was moving. I recently relocated from Washington D.C., the Washington D.C. area, more so Maryland, to Fargo, North Dakota. And I've been, horribly busy, just getting myself acclimated to one the horrible weather, but also just navigating a brand new place, trying to meet new people, just trying to get myself out there first and foremost. Um, as some of you know, my whole goal is to um, go to graduate school and go to graduate school in order to study um, plasma physics and laser physics. My main research interest is in solving primarily solving the energy problem from a particle physics perspective. And so with that in mind, I was busy. I was extremely busy, and then plus the move meant that I didn't have access to a board, and now I have access to a brand new black wood whiteboard. It's sweet. I really like it, and I will be uploading more regularly, or I will be uploading to the as a schedule that was indicated long before in the other videos. Uh, this video is going to be dedicated to solving, for the first time, finally, plasma physics problems. The book is Fundamentals of Plasma Physics by J.A. Bittencourt. It's a pretty good book. Um, the text is the text is the text is very comprehensive. I will be doing lectures on this book and on the chapters because I feel like without the lectures, a lot of it won't make too much sense. A lot of the problem solving won't make too much sense. So I will be doing problems out of this book. I also have some brand new books that I want to do. I wanted to start up a section on pure math, and I'm going to start out with differential equations slash calculus. So I'm going to be doing both of them simultaneously. We're going to be doing some basic calculus problems, starting out with limits and things. So this part of the video is more so like where I want to take the channel. I'm going to be getting into problems in plasma physics in just a minute, but yeah, I'll be doing limits from calculus, going into derivatives, and then moving from derivatives to integrals, and then finally, into differential equations. But I'll be taking sections out of calculus books and out of calculus, from calculus problems on the net, and doing those for you guys. I might do some lectures on those. I'm not exactly sure as to how much time I'm going to be able to have doing lectures on plasma physics, but then also doing lectures on calculus. It's going to be a bit rough. Problems in thermodynamics. I will continue to do those. There will be a problem set uploaded tomorrow afternoon slash morning. I wake up around like 5 o'clock in the morning because I can't sleep here. Um, so yes, sometime tomorrow morning, maybe after work. And then on Saturday, I will have chapter 3 of the electrodynamics problems uploaded, or the graduate electrodynamics books uploaded. I have other books that I wanted to talk about. One other one that I probably do like once a Sunday, do a lecture and then do the problems on curvature and mathematical physics. This is a mathematics and physics. This is a pretty good book. It's very difficult. It's difficult even for me. I think it's more so a book that's more suited for graduate students than it is for undergraduate students. Modern or undergraduates nowadays don't really have access to a lot of set theory unless you were a mathematics major. But even with the set theory, I didn't focus too much on it. I focused more on skills that a mathematician uses. to solving problems and more so towards physics problems. Whew. Excuse me. I have to take a sip of my nightcap. It's late. And I had a really, 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 really long day. Let's get into the problems. So, with plasma physics, chapter 1 of plasma physics, Bittencourt gives us problems that are more computational than computational and review, rather than jumping into, like, what is a plasma? Define plasma in your own words. Those are good problems, but for undergraduate students and for graduate students, those aren't very helpful. If you just give people the definition, that is much more valuable than asking them to like define things that can only be defined by various variables. For instance, I'm looking for my marker. Excuse me. Oh, first of all, I didn't introduce the new setting. As you can see, not only do I have a new whiteboard, but I'm recording in a brand new, or my new apartment in Fargo. I said I moved, but I didn't really introduce, the layout. This is more so gonna be the layout from now on until I get bored of it, or until I find a place where I can like stand up and do these videos. But I have a brand new 2-bedroom, and I'm very happy with it. I love my apartment. I especially love the closets. I love walk-in closets. Anyway, back to physics. So Bittencourt gives us these, introductory conceptual problems, computational problems that ask us to like look at various, various plasma-like particle interaction-like problems, and just review skills that a physicist will need to help solve problems in plasma physics. And this is also one of the reasons why I plan on doing, a calculus section, and especially a differential equation section, is because solving differential equations will be extremely important in the later chapters. For one, you'll have many different coupled differential equations, and by coupled I mean you'll have multiple variables, or two or more variables, um, in a differential equation of another variable, and you'll have a system of differential equations in which you have to manipulate them in order to find out, how the system behaves as a whole, as opposed to, individual directions. And so this is a good introductory chapter. It's a good intro to questions, and I'm going to do a couple of them. We're already at the 8-minute mark, so let's jump into it right now, shall we? So the first problem, Bittencourt asks us to, he gives us a little bit of background. I will be doing a lecture on chapter 1, mind you, but just bear with me as I do these problems. In chapter 1.1, or problem 1.1, Bittencourt says, the interatomic or intermolecular forces are usually represented in terms of a potential energy function. And we typically define that potential energy function as V of R or U of R. Some people write U of R, and that's V of R. And this is a potential energy. And what is a potential energy? A potential energy function is it's just how it's typically how you describe conservative forces, but it just describes the forces of a system, or the information of a system from an energy perspective. And you can describe the forces acting on the system by where this triangle system, this triangle um, represent this upside down triangle represents del, which is a gradient operator. And if you don't know that by now, then I can review it later. But if you're looking at plasma physics problems, then and you don't know what del is, well then, um, give you a definition of del. Um, del in Cartesian coordinates is where these are partial derivatives in the x, y, and z directions, and these are the unit vectors. And for spherical and cylindrical and various other coordinates, you then have to do the various change of variables in order to find what del is in those different coordinate systems. But del is a partial derivative operator. In general, it's written as such. Um, there. In general, like a general way of describing it, or a tensor way of describing it, is like as so, which is in Einstein summation. It's in Einsteinian notation. This describes a summation. Blah blah blah. I go through this in the graduate electrodynamics book. I don't really want to go over it in the plasma physics book. Anyway, so for neutral particles at large internuclear distances, there's a slight attractive potential between particles called the van der Waals potential. Um, and so he's giving us some information here. So Bittencourt is saying that these neutral particles have an intermolecular force called the van der Waals force that attracts them to one another. And he says it's the long-range part of the Lennard-Jones potential. For like atoms or molecules in the states of in like states, the van der Waals attraction potential can be represented as, excuse me. I like music, and the music that is playing is Vivaldi's Four Seasons. This potential can be written as C A0 over R 6 power Ry, where C is a constant, A0 is a constant. C0 is a constant that depends on the actual molecules in question. A0 is the I think this is the Bohr radius, and Ry is the Rydberg energy constant. I'm going to write down some values. A0 is approximately, yes, it is the Bohr radius. It's 0.05 times 10 to the minus 9 meters. And Rydberg is, yeah, famous constant, approximately 13.6 electron volts. And so Bittencourt is asking us to calculate the van der Waals force of attraction between two hydrogen molecules for which C equals 24. So for the hydrogen molecule, C equals 24. And so what is the van der Waals force? The van der Waals force is obviously, given by this definition, going to be the gradient of V, which is just a derivative. And in spherical coordinates, we're lucky because we don't have any azimuth or polar deviation. So we only have to look at the derivative in the radial component, which is very sweet. It makes things a lot easier. So what is this? This is going to be minus 6 times C A0 over R. This is to the 5th power now, because it's a derivative. Bring that down, subtract by 1. And then we take the derivative of the function on the inside, which is going to be A0 over R squared. But this is times a minus 2. And it's times the minus 2 because there's a derivative of an r to the minus 1. So subtraction is therefore going to be. Shit. You do. Sometimes I forget. You bring it down and then you take the minus. You bring it down, you take the minus 1, you take the minus 1, and then you bring it down. Sometimes I screw that up. Think. You know how. See, it's been a second since I've taken a derivative. Believe it or not. Sometimes it just you get a brain fart. So you know how I do it. Just dx of what x is. That's 1. d dx x squared makes this nice easy. 2 regular x. So you bring the 2 down and then you subtract. So this is not going to be minus 2. This is going to be minus 1 times Rydberg. And there you go. There's your 2 there. So cool. We're moving forward, and we're moving at a much better pace. So this is going to be positive. So you have 6 times this function, and then we have an extra r squared in the denominator with an extra just a to the first power. So that gives force van der Waals equivalent to 6c Rydberg. What we can do is we can divide by a0 and say that this is now a squared, so that this is now this both of these both of those parts of our function add together evenly. We have r, and then we have a 7 here. Just makes things a little bit easier to deal with. So this is our force van der Waals. And then we already have our numbers there, so we don't really have to worry too much about anything. And actually, we can approximate this a little bit more to make things just a tad bit easier. We can say that this is 14. 13.6 is closer to 14. Yeah, 13.5. I mean 13 anyway. So we said this is, approximately 14 EVs. This is approximately, I know that, double approximation is a bit, double approximation really is, it's a bit of a no-no. We don't do it in physics. One approximation should be more than enough. You don't really approximate an approximation. If you're saying something that's already close, you're kind of screwing. This number is already close to the one that's given. You're already screwing up a function to some extent, probably to like a hundredths place. But then by doing it even further to a tens place, because I'm going to make this a 0.1, you've already screwed it up 1,000, like to 1,000 order. This is going to be to a tens place, and we've already screwed up to a, this is hundreds, 1,000, so something along, a 10,000th of an order. And for particular numbers, especially when it's already small, to the 10 to the 9th, it kind of adds, not adds, but you kind of tack on too much of an approximation, and it really does screw up your computations. But because this is just a basic, not a basic, but this is a somewhat of a homework problem, a toy model, we don't really have to worry about that sort of thing. So 0.1 times 10 to the minus 9 meters. This is 14, and that's 24. We don't have to approximate 24. 24 is fine. So here's our force. And the reason why I approximate this even further is because we're not really done with our problem. Because Bittencourt then asks us to compare the van der Waals force with the Coulomb force between a proton and an electron at a distance of r equals some number times the Bohr radius, where n, that some number, is much greater than 1. And so, what is the Coulomb force or the electrostatic force for proton and electron? Well, easy enough. Force Coulomb is minus E squared over 4 pi epsilon naught. Damn, I don't remember. I put last time I did this problem, I put the 4 pi up top, so I didn't remember that very well. N A0 squared. Boom, done. That's the electrostatic force between, an electron and proton at a close enough distance, or at some distance. And because the force Coulomb is conservative, you don't really have to worry about whether or not, your tangential or whatever. It's a radial distance away. And we're assuming the same for FB. So cool. Cool. Let's compare. Well, before we compare, what I want to do is I want to look at something first. I want to look at, just what are we supposed to expect? And lucky for me, oops, I screwed up my damn book. Lucky for me, I've had the opportunity to see what the Coulomb and the van der Waals potential look like. And here we go. Coulomb force, well, most people, if you're looking at these videos, the Coulomb potential looks something like this. This is not a very good approximation. This looks more like the Coulomb force than the Coulomb potential, but close enough. At really small distance r, or radial distance r, you have really high potentials. And then as r increases, you steadily go to points where the potential is 0. And for the van der Waals potential, well, first and foremost, it's negative. And then r decreases to the 6th order as opposed to the 2nd order. And so what you have is that, at 0, you have negative infinity, and it goes up very quickly, and it much faster goes to 0 than the 1 over r squared. This potential goes to 0 a 4th order, or 4 times faster than 1 over 4 times faster, or a rate of 4 orders faster than the 1 over r squared. And so what are we supposed to expect? Well, the superposition, or the summation of these two functions looks something like this. At really small distances, you have the positive. You'll have a positive order here, but then it'll go negative at some distance from r, and then eventually come right back up to x equals 0. And this term, because it goes to 0 much faster than this term, will die off much faster. So you have this dip here. And so what are we looking for? Well, we're looking for if n, because r equals n a0, if n is so much greater than 1, we're looking for distances of r in which f of v is much greater than f of c. We're looking to show that f of v is much greater than f of c at even really large distances of n, simply because look how fast this function goes to 0, and look how much it dominates at long distances. These are really short distances in which the 1 over r, not 1 over r squared, but the 1 over r function dominates. Look at it, it's positive here, but then it slowly and steadily goes to 0. But look how quickly this goes to 0, and it's negative. and then only slight distances away from the 0 point of the radius, you already have this negative function, and then it still dominates and quickly goes to 0. We're looking to prove that f of v is much stronger than f of c. And we were already told that it's a long distance force. So how do we do that? Well, we divide the forces. We're going to keep these approximations, but we're going to also keep our forces here, because these are very important. Now, I'm not going to do the computation. I'll show you what you should expect, but I don't feel like I actually did the computation well enough in order to showcase it. This is my University of Maryland Day shirt. So I'm going to be using it as my eraser for a while. For one, even though I'll probably still be using it, I don't have anything else to erase with. So magnitude of FV over FC looks something like, well, 6 CRY times 4 pi epsilon naught n A0 squared. The inverse of this thing is divided by over E0 A0. Actually, really, this is a to the 8th, because this is divided by this will be, whoops, nope, this is not a to the 8th. This is A0. A0 will be in the 7th order because it's up top, FV, and then R to the 7th will be in the bottom, and A0 to the 7th. And so, what do we have here? Well, we can get rid of U, get rid of order of U, put a square there, and these are all constants. The A0 is a constant. It's 0.1, 10 to the minus 9, so it's really 10 to the minus 8. It's 10 to the minus 8, so 10 to the minus 8 to this raised to the 7 will give you 10 to the minus 1, which will give you a 10 up here, so maybe like a 60, and then you have another 10, well 10 to the minus 10 minus 10, so you have other orders of things. You can knock this out here. So you have n to the 7th, A0 to the 6th. So 10 to the minus 8. 10 to the minus 8 times 10 to the 6, which is 10 to the minus 2. So this is going to be 600 times 24 times 14. 4 pi epsilon naught, again constants. Epsilon naught is like 10 to the minus 19 or 10 to the minus 34, something of that nature. But that kind of is this is kind of dominated by the 10 to the minus 38 here. So you'll have a really small number down here, but you'll have a 10 to the 7th. I mean, an n to the 7th and an n squared up here. So this is gone. And so then all you have is an n to the 5. You have an A0 to the 7. Knock that down, so you just have an A0, which is 10 to the minus 8. So 10 to the minus 8, you don't have a 600 anymore, so you have a 10 to the minus 8, 10 to the minus 34. Trying to think. What is this? 10 to the minus 38? Because it's 10 to the minus 19 squared. So 10 to the minus 38. So 10 to the minus 38, 10 to the minus 34. So this is 1,000. This is 1,000. This is a big number up here. And so if you say that this is 1,000, and so you have 1,000 times 4 pi 6, all these positive numbers, so you get something along the lines of like 10,000. So you have a 10,000, and then you have an n to the 5, and n is much greater than 1. So let's say n is 10 to the 6. So then there's 10 to the 6. This is 10 to the 30. 10 to the 30 over 10,000. This dominates, obviously. And this says, can we get a good number? That dominates, obviously. 10 to the 6, it's a 10 to the 30. Is this much bigger than I think it is? I'm not sure. I think this is a small number. If it's a small number, this is a small number, and that's supposed to balance out the coulombs into newtons. I'm not sure. In my notes, this is supposed to dominate completely over n to the 5, even at 10 to the 6. And that would make sense because that was the whole point of this diagram here, is that this is a long distance force, so it's supposed to dominate the Coulomb force for much longer distances. We definitely can do the computation. Just have to figure out exactly. This is 10 to the minus 38. So if this is 10 to the minus 38, and let's say that this is 10 to the, I think this is 10 to the 20. So this is 10 to the minus 58. So really the 10 to the minus 50, and then you get 6, 24, 14, 4 times pi, and then you have 80. That's in the 5th. It's 30. So this is 38. It's 20. It's 58. So this is a 50. And even if this is, because this is 10 to the minus 8, it's 10 to the minus 8 meters. So even if this is 38, that's 20. That makes 50. This still dominates the end of the 5. So that proves that f of v is much greater. So this is like something around 10 to the 50 over n to the 5th. And the only time that this is the Coulomb potential is going to dominate is when this is 0 or less than 1 and start becoming infinite. And at the larger distances, you're going to need like significantly larger distances, something along the lines of n is 10 to the 10. And then you get 1, so the forces balance out when n is 10 to the 10. But by that time, f of v is 0. F of v is practically 0, and then the Coulomb potential is practically 0 because it's extremely long distance. So you wouldn't even really consider it, would you? At a10, n is 10 to the 10, and a is 10 to the minus 8. So what is that? It's almost 100 meters. 100 meters worth of distance for an intermolecular force is practically zero. Alrighty. So the next problem, said I wouldn't go through the computation, but I did show more so. Yeah, I'm not writing down the actual me doing calculator math, but I did show exactly what I wanted to show, that van der Waals force is x long distance and dominates the Coulomb force for long distances. And so Bittencourt gives us in 1.2, this is going to be the last problem of this video. 1.2, he gives us this slab of plasma, or this particle slab, in which it is electrically neutral, and at these two distances you have positive ions and negative electrons in close proximity, in which the electric field is zero. But then we're asked to look at a perturbation of the electron or the electrically negative part by a distance x, and to find the electric field of this perturbation. And how do we do that? Well, how do we find the electric field of this perturbation? Well, we use Gauss's law. And if we use Gauss's law, we're going to use a Gaussian pillbox, which is rectangular in nature. And we're going to say that, well, if we look at the whole pillbox, the flux outside the pill, we'll look at the whole length of this this material, this electrical material. We see that the flux downward in the z direction and the flux upwards in the top will be the top portion of this box. Zero. So electric field, there's an equal amount of electric field leaving as there is an electric amount of leaving downwards as there is an electric field leaving upwards. And then we can say the exact same thing for the y direction. Field this way equals the field that's leaving that way. But what can't we say? We can't say that the field that's leaving in this direction is the same as the field that's leaving in that direction, because we don't know exactly how much of the electron material is actually inside of it. We know that there's an imbalance of charge. There's a charge imbalance. It's not evenly balanced in the electron. We're assuming that it's not evenly balanced in the electron charge. So what does Gauss's law state? It says that the divergence of E of the electric field is equivalent to the total charge enclosed by the Gaussian surface divided by epsilon naught. And the total charge enclosed, because all the charge is negative, is minus the number of electrons times the electron charge. We don't know how many electrons are in here. We just know that there's an imbalance divided by epsilon naught. And because we know that the electric field is only in the E direction, we're looking at the divergence of E sub x. Therefore, the total electric field is minus NE epsilon naught x, plus a constant, but we can always say that constant is 0. It's just a slight imbalance in the electric fields. How do we prove? I don't feel like doing that. Proving that, despite us doing a partial derivative, so an integration of a partial derivative, that if you add a constant to a potential, or you add a constant to an electric field, and then you take the derivative, if you look for the potential, you can always say that that's you know, by the initial conditions and everything, that constant zero, or that at some point that constant can be, understood as a 0 point. Just take my word for it, is that we don't need a constant there. Please take my word. And so we found the electric field, and Bittencourt asked us to show that the equation of motion of, Newton's second law for each electron under the action of the electric field is given by this statement. So he's asking us to find the equation of motion for, for an electron in this distribution here, in this perturbation of our, of our electrical material. And what does that look like? He says that it's given by n e squared epsilon naught x, there's supposed to be an m, equals 0. And so this is easy enough to prove. We look at the total forces acting on some electron in this electric field, and that has to be given by, where's the electric field, minus n e, because what is the electrostatic force? The electrostatic force is, the charge times the electric field, and in this case the charge is E. Actually, it's minus E, and you say an electron motion for each electron under the electrostatic field. So technically, it's plus, and this has to be equal to the mass of the electron times the second order derivative of its position. Actually, I'm pretty sure that Gauss's law gives us a negative here, and that negative is supposed to go, there's a negative here, and there's a negative here, so that negative goes there, makes that positive. So then there's supposed to be a minus sign here. So I was wrong by minus sign. I had to look at it a little bit, because I'm pretty sure that there's supposed to be a minus sign there due to Gauss's law. This minus sign is due to the fact that we have a negative total charge. This minus sign is due to the mathematical nature of Gauss's law. I know I'm cheating the audience a little bit, but just bear with me. Like I said, today was a long day. So what do we got? We got the equation of motion. Add quantity to both sides. Divide by m. X double dot equals n over m e squared epsilon naught x. Booyah. Add both sides. Equals 0. So that is exactly what was given. And then we're asked to show that, this looks like a harmonic motion solution, and that the harmonic oscillator has a frequency that's the square root of this sucker. And so how do we go about showing that? Well, we solve the differential equation, and this is a harmonic oscillator sort of solution. And how do I look at it and see that it's a harmonic oscillator? Or in this case, simple pendulum motion or harmonic oscillator, however you want to look at it. I'd look at the solution for sort of like the pendulum bob equation for the pendulum bob problem. If this is the vertical, this is the tension in the wire. And is that the mass? So, is this the force of gravity? The force of gravity is downwards, right? Yeah, the force of gravity is downwards, and there are two components. That you have your radial component that's keeping, that's keeping the pendulum from either bunching up the string or the tension, and then also is the tension is also pulling against gravity, which is mg cos theta minus, and then you have this radial component, which is, pushing and pulling the pendulum back and forth towards its equilibrium point at the center, which is mg sine of theta, or phi in this case. We're going to say it's phi. And so, as I said, this mg cosine theta completely cancels out with the tension component. So the total force that's acting on this mass here, this pendulum bob, m, is the mg sine theta. So what do you have? You've got total force equals mg sine theta, and for small degrees, typically less than 50, 0.5 degrees, or 0.5 radians, something like, I think it's 0.5 degrees. You have sine theta is equivalent to mg, just regular phi, and this total force is the periphery, or the arc length, derivative of the arc length of the path that's swung by the pendulum. This is the tangential component. The tangential component is all along this arc length, which is m, which is the mass, times L, which is the radius of this mass. So actually it's not this, but it's more so this, excuse me. The radius from, the pivot point times the angular acceleration. And the angular acceleration, ml phi double dot. It's the second derivative of phi. Well, finish it up, you got g over L phi minus g over L phi, and psi double dot is equal to 0. And well, this is obviously very similar to this equation here, set by a minus sign. And that minus sign can easily be rectified. Can easily be rectified or understood in the sense that, from a harmonic oscillator solution, this is sufficient as cosine of omega t plus phi, and this is sine of omega, say, prime of t plus phi prime. And the difference between the signs is just the phase. So really these equations are describing the same thing, there's just different phases, depending on how you write, in the direction that you write your mg sine theta. It really doesn't make too much of a difference. But this solution is indeed going to give you the square root of, n over m, e squared over epsilon naught is going to give you your omega term. Just solve the differential equation, you'll realize that it's just as simple as that. So those were the first two problems of the introduction of plasma physics. I will be doing more problems, and they're going to be much faster than these. But in the meantime, This was a sound introduction or sound revisiting to basic skills that you should have already acquired in terms of, before you attempt to follow me further in this book. Um, I know it's been a long video, and I apologize for how long it's been. It takes me a second to explain everything and then read the problems. I'm not going to read every single problem in the future. But in the meantime, I will be doing these a little bit faster. Videos shouldn't be longer than 30 minutes after now. For me, the first couple problems are going to take a second just for me to get folks acclimated to how I'm thinking about problems and how you should be thinking about solving these problems, how you should be looking at them, especially when you see things like this and you have to compare them to things like this. And really, they're the same thing. It's just the difference is a minus sign right there. Say that, we kept the minus sign. Well, there you go. You have your same solution. And the difference is just a phase. The difference is a phase, but also the magnitude of your frequency. But, difference is just a bit of a phase because they're still describing sinusoidal functions, or the differential equations still have solutions in the sinusoidal plane. Sinusoidal plane, but the complex plane. So thanks for watching. It's been a minute. I'm going to get myself reacclimated to solving these problems. I'm going to be getting videos out. They're going to be faster. They're going to be a little bit funner. Right now, they're a bit boring. It's going to be a little bit boring, but once I get the lectures out and folks start understanding shit, we're going to get this ball rolling, buddy. See you next time. Or see you in a few. Once I put out part 2 of chapter 1 of the fundamentals. Bye-bye.